In this video, I want to give you a demo of tracking down and fixing memory issues in your app. We're going to take a look at how we can debug memory issues, but before that I want to give a little introduction to strong and weak references, which is an important topic to understand in order to be able to fix memory issues. Swift has two main types of references, strong and weak ones. Let's take a look at an example of strong and weak references. In this example, we have a person, a wallet, and a credit card. Strong references indicate ownership, and weak references are just simple references, but not owning ones. So in the context of this example, some external resource owns the person. The person owns a wallet. The wallet has a reference to the person. You can imagine, for example, a sticker that has the address where the person lives, but the wallet does not own the person. So therefore, the connection between wallet and person is a weak reference. The person, however, does own the wallet, and therefore we have a strong reference. The wallet also additionally owns a credit card, and therefore we have another strong reference between the wallet and the credit card. Objects in Swift stay alive as long as there's at least one strong reference to them. So if our program removes the strong reference to the person, then the rest of the object graph will resolve, because all of the objects are dependent on the person. We remove the reference, so now the person is no longer referenced and will disappear. Since the person is no longer there, the wallet, which is strongly referenced by the person, and all the references of the wallet will also disappear. Finally, since the wallet disappeared, there's also no more strong reference to the credit card, and the credit card will disappear as well. This is the behavior we want to see in our apps. We have strong and weak references set up correctly, and if the object that owns all other objects, all dependent objects, disappears, then all these dependent objects disappear as well. This means the memory gets freed and our application works as expected. In some cases, we make mistakes, and we set up strong references that actually should be weak. Here we can see an example of such a mistake. We have exactly the same situation as earlier, just the reference from the wallet to the person is now by mistake a strong one and not a weak one. So if we free the reference to this person, we would expect the person to disappear because there's no more strong reference to it. Let's walk through this example. We again free the reference to the person. Now we would expect the person to be removed. But unfortunately, this incorrect connection, the strong reference from the wallet to the person, keeps the person in memory. Now we have an island of three objects, the person, wallet, and credit card, that cannot be referenced by any other part of the program, but are still remaining in memory. This is what we call a memory leak. If you create multiple of these leaks, then we have more and more objects that are unreachable, but still remain in memory because they create strong retain cycles. This is a typical problem in many iOS apps, and in a later part of this video, we're going to take a look at how we can identify these problems and fix them. Now, moving away from this abstract example, I want to show you which kind of concrete examples we have for strong and weak references in iOS apps. This here is one of the most common examples. It contains a view controller and a table view. Some outside resource, for example a tab bar view controller, has a strong reference to the yellow view controller here. The view controller owns a table view. Therefore, we have a strong reference from the view controller to that table view. The table view also needs to communicate with the view controller because it's its data source and delegate. These are both weak connections. The table view does not own the view controller. It just needs a reference to be able to communicate with it. So this setup here is correct. However, later, when we take a look at a demo app, you will see that this pattern is also a common source of errors. If, for example, you set up the delegate connection to be strong instead of weak. So it is important to understand the concept between strong and weak to be able to avoid such issues. Essentially, the difference is pretty simple and straightforward. Strong references indicate ownership. If you do not own an object, or you have not created that object, you most likely don't want to have a strong reference to it. If you just need to communicate with an object that already exists because it is owned by another part of your code, then you want to use a weak reference. A weak reference is just a reference. For example, the name tag inside of the wallet that refers to the person. And in case of iOS apps, for example, the delegate or the data source on a table view. The table view needs a way to communicate with these two components, but it does not own them. Now that we have a basic understanding of strong and weak references, let's take a look at a demo app that has a memory issue, and let's find out how we can fix these issues using Xcode tools. If you want to follow along with this video, you can download the example project that we are going to use from our GitHub account. Here you can see our simple demo application that has the memory issue. It is really straightforward. It only has a button on the main screen that allows me to push a view controller, and I can hit a back button to return. Now I realized when I do this multiple times, the app really slows down at a certain point in time, and then it even crashes. So if I have the suspicion of a memory issue in my app, the first thing I can do is inside of Xcode take a look at the information about the memory usage. If you open this debug navigator over here, you'll see basic information about CPU and memory usage. Now, what we want to find out is, does the memory usage or the CPU usage increase when we use the app for a longer period of time? So what I'm going to do is repeat the step over and over again and see how it impacts the performance of the app and how it impacts the metrics that we can see over there. And if you look at it, it seems like the CPU is pretty okay. We always fall kind of back to 0% CPU utilization, which is good. But we have issues with the memory. Memory is increasing every single time that I push the view controller and pop it again. So now we started at more or less 10 megabytes, and now we're nearly at 20. So we definitely have an issue there. Now in this simple application, it would be fairly easy to just take a look at the code and track the line down that actually causes the issue. However, I want to show you an approach that also works for bigger apps where you can't just read the entire source code. We actually need to narrow down the problem using Xcode's tooling. Before we dive into the tooling, I'll turn on the mouse per indicator so you can follow my mouse. The tool we have seen over here is really very simple. It only shows us CPU and memory usage. It's good to find out initially if you have a memory problem, but it isn't helpful in tracking the memory problem down. For that, we have a tool called Profiler. So let's stop the application, and we're going to start it in the Profiler. Before that, we will change a setting that is important. Open the button up here, and then go to Manage Schemes. Now double-click on the only scheme you have, and then we're going to go down to Profiler. Now we need to change the build configuration that is used when Profiler runs. Xcode has two different build configurations. One is debug and one is release. Typically, when you run your app in a simulator or on a device, it runs in debug mode. And that means there's additional information attached to the program that makes it easy to find out, for example, which current line of the program is running or which line of the program crashed. All of that additional information is not available in release mode. It's basically a more efficient version of the same app. If we want to debug a memory issue, it's much easier to do so if we do it in debug mode, where we actually have all the additional debug information provided to us. So we select Profile and we change the build configuration to debug. Once that is done, we can actually launch the Profiler. One important aspect with the current version of Xcode, which is, as of this video, version 6.4, it is not possible to use the Profiler to full extent on the simulator. It unfortunately has some bugs. So for the purpose of this video, we're going to run it on the device. Once you have selected the device, go up and select Product, and then Profile. Now your app will be compiled, and then the Profiler window will come up. Profiler is a tool that allows us to inspect a variety of metrics of our app while it is running. We have different things, for example, energy usage, or how many animations are used, or the activity monitor that indicates how much CPU usage is going on. For the purpose of taking a look at memory allocations, we typically choose the Allocations tool. So for now, we're going to select Allocations and choose. Now you see a new window pop up. This is the actual Instruments tool. We can start our app by hitting the Record button. As soon as the app starts up, Profiler will provide us with information about the memory usage on this timeline up here and in the table down here. Before we get started, we're going to change one more setting. On the right-hand side in the leftmost tab, you want to activate Record Reference Counts. This option here will mean that Profiler will actually keep track of every single reference count. It means every single strong and weak reference that we create throughout our code. That can be very important when tracking down memory issues. And later we will dive into how we use these reference counts to identify and fix the memory issue. Now we have configured everything to get started and actually run this app. So let's hit the record button. Now the app will start up. And as soon as it is loaded, the simulator will appear or the app will launch on the device. Over here you can see the app running on the device. Now the first thing we need to do is actually reproduce our memory issue. So in this example, it was pushing the view controller and popping it multiple times. We're going to do this over and over again. We're going to see how the graph behaves. You can see that we have an increasing amount of memory that is being used. It is growing and growing over time. Typically, when you use an application, you have growing memory at the startup, and then after that, you will have a flat memory curve. If you see any curve like this one here, it typically indicates that you have a problem, especially if it keeps growing over time if you perform a certain action over and over again. So in this example, we can see the memory usage is now at 12 megabytes. To actually isolate the problem, it's important to increase the memory usage a little bit more, so that the one single source of the problem becomes more obvious. Later, we will take a look at a graph that shows us which part of the code is using how much memory, and the longer we perform this here, the more obvious the part that actually has the error will become. Okay, so now we doubled our memory usage to 24 megabytes. We can now take a look and actually pause the app and inspect the values that we got. Let's first take a look at the graph. The graph again shows whenever we popped the view and added it again, our memory usage increased. Now we are certain that we have a memory issue. But how can we track down which part of our code exactly is responsible for this problem so that we can fix it? The best way to get started is taking a look at the call tree view. The call tree view breaks down the memory usage of our app per line of code that is running. You can see at the top, we have 100% of the memory used. And as we expand the call tree to see which different subroutines are running, we will see how much percentage of the total memory they're using respectively. We can do this until we find the part of our code that is using the most memory, and that is most likely the part of code that is causing the memory issue. Now you can see there are a lot of system calls inside of this call tree. All of these functions are called by the operating system, but they're not our code. Since we strongly assume that the issue is actually in our code, we want to ignore all of these system calls. We can do that by selecting the middle panel over here and select Hide System Libraries. Now the call tree gets reduced to only our functions. Here you can see that we have one function that stands out, using almost 20 megabytes of memory and almost 82% or almost 83% of the total memory usage of the app. So this line of code here is most likely responsible for the issue. You can read which one it is. It's memory issue demo, image view controller, view.load. If you want more details, you can double click onto this line and it will be highlighted inside of the editor. So this view.load function here is responsible for most of the memory usage. Sometimes Profiler has a little bug and it doesn't show you which line exactly causes the issue. Usually it will highlight the percentage per line in the side of this view. So here we have two lines that look fairly suspicious. What do we do? Well, we load a file. And I can tell you I've already inspected this app. This file here has more or less 1 megabyte of content. So since the memory is increasing 1 megabyte every single time we push this view, it seems a little bit like this line of code here is actually causing files to be loaded that are then never freed. Why would these files stay around? Well, let's take a look at what we're doing. First, we're creating a local variable called file path to get a path to the resource. Then in the second line, we are downloading or actually loading the actual content of the file using NSData contents of file. This here loads more or less 1 megabyte of data into memory. And then we assign this to a data variable. And if you check out where this belongs to, we can see that this is a property of the image view controller. So it seems like this data property here is holding a file. And if we load another file, then that is also stored inside of the data property. All files we ever load somehow seem to stick around. So most likely we have a retain cycle somewhere. The data property itself is not very suspicious. As soon as the image view controller disappears, the data property should also disappear. We can be confident about that because we know that there's no other reference to this NSData block here. It is really only this one property. The class here is very simple. There are no other references to NSData that would make it stick around. So if this property itself is not a problem, then it means that the container, the object that actually contains this property, is responsible and causing the issue. So maybe something is wrong with the image view controller. With this suspicion, we can go to a different view and try to find out if we can get more information. So let's copy this class name here and then go back to the statistics view. Inside of the statistics view, inside of the search field, we can search for different class names. In this case, we want to see the image view controller. And we actually get one result. Now, there's a lot of information in this line that is really important. We can see the total amount of objects that have been created, the amount of objects that are currently alive in the persistent column, and in transient, we see the amount of objects that have been destroyed of this type. The interesting aspect is this is the view controller that we push onto the stack when we hit the push button. And when we go back, we actually pop it from the stack. That typically means that a view controller should be deleted. However, we have 29 instances of which 0 have been deleted. So somehow, even though we pop that view controller from the view controller stack, it is not being deleted correctly. With this information, we can dive into even more detail. So we now know that the view controller is not released correctly, which means we must have some kind of retain cycle that involves the view controller. So let's hit this arrow here to get some more information. In this view, you can see information about all the instances of the view controller that have been created. That allows us to dive into more detail. Firstly, we can see the different timestamps. For example, you can see that the very first view controller was created 20 seconds after the app launch, but it still sticks around. And the latest one was created 1.5 minutes after the app launch. Now we really want to know why these instances are still in memory, even though we actually popped them from the view controller stack, and they therefore should be deleted. Since all of these objects are created in exactly the same way, we can select any of them to inspect more details. So let's just select any view controller and jump into the detail view. Now, because we have recorded all of the reference counts, we can see every single reference that has been created, and we can see whether it is a strong one or a weak reference. This can help us in tracking down which part of our code is keeping a strong reference to this view controller and therefore keeping it in memory. Now, this is a very long list and it can be hard to parse through it, especially if your app grows more complex. So the first thing we can try is filter by unpaired calls. This will filter the list of calls to only show the ones that instruments cannot really group together. Group together means that it is obvious that object has been created with a strong reference, but that strong reference has been freed immediately. For example, if you assign an object to a local variable, and the function ends, then that local variable is freed. And it's very easy for instruments to detect that you have a paired or grouped call in that case, where creating and removing the strong reference match up. Now we can see all the ungrouped ones. And if we actually have a memory issue, then we're definitely going to have an ungrouped call at some place. The second way to filter this list is ignoring all of the lines that show system libraries. For example, UIKit. And we actually want to find one that shows our app name as responsible library. So we're going to scroll down this list, and here on line 55, you can actually find a call that is done in our code. So this is one line of code that actually creates a strong reference to this view controller. And we can see that because the keyword here is called retain. Retain says create strong reference. Release says remove strong reference. Now if we scroll to the bottom, we can see that there's no other call inside of our app. That means there's no release call for this retain call. And that means that the strong reference is created to this view controller, but it's never freed again. So who is creating the strong reference? We can expand this here to get an idea, and we can see that this strong reference is created with inside the viewDidLoad method of the ImageView view controller. That is really suspicious because that wasn't really obvious. So inside of viewDidLoad, we're creating a strong reference to self. Let's take a closer look at the code again to see where this match could happen. We now know that the issue is definitely within this method here. And someone is creating a strong reference to this view controller. So let's take a look at it line by line. The first line is very unsuspicious. We just call super viewDidLoad. Second line, we're calling leakyImageView.delegate and setting ourselves as the delegate. This line could potentially have problems. Because we're passing self around, there is a chance that this image view here is actually creating a strong reference to this view controller. And if we look at the last line, which we already inspected, we see that we're just loading a file. So very likely the issue is within this line here. So let's jump to the definition of this delegate. Okay, so what we can see here is a variable called delegate of type anyObject. What could be wrong here? Well, the issue is this here, by default, as every variable in Swift, is actually a strong property. Earlier we learned that delegates actually always should be weak references because they're not owned references. The image view doesn't own the view controller. It just needs a way to talk to it. So in this concrete example, what is happening is the image view is a child of the view controller, and therefore the image view stays in memory. Now, when the view controller shall be removed from memory, it doesn't actually get removed because the image view is still holding a strong reference to it. And because the view controller is never removed because of the strong reference from the image to the view controller, the image view is also never removed because there's also a strong reference from the view controller to the image view. So the image view and the view controller are both referencing each other strongly. And that is what we call a retain cycle. We have two objects that create a strong relationship between each other, and therefore they will always stay in memory. Doesn't matter what happens around them. So this is actually causing the issue in our case. I'm pretty sure. So let's fix this here and turn this into a weak variable. Now we can try and run this app again and see what happens. And we can actually run it on the simulator now, because all we want to do is verify the memory usage. And if the memory usage over here is fine, then we don't have to open Profiler anymore. So let's see if this here solved our problem. We're starting with a memory usage of 11 megabytes. Now we're pushing, popping, pushing, popping, and we repeat this over and over again. Now we have identified earlier that the memory was growing by more or less 1 megabyte every time we pushed and popped the view controller here. Now we have done it multiple times, and we can see that the memory usage is still constant. So we're now still at 12.4 megabytes, which is only slightly higher than at the beginning. But you can see it doesn't matter how often we push now, the memory level remains constant. So now we have resolved this retain cycle by creating a weak reference from the image view to the view controller. That means the image view no longer retains the view controller, and that means the view controller can now disappear from memory, and when that happens, it also removes the image view. I hope this example was helpful in showing how to debug memory issues, and if you find some in your app, come back to this video and try to apply the techniques that we learned here.